The multimodal transistor is a new device that borrows from a long history of advanced semiconductor devices for thin film technologies. We have chosen to demonstrate it with a thin film technology which was highly mature in order to best show the functionality of the device. I'm Radu Sporea and I'm a senior lecturer at the University of Surrey.
My name is Bestelink. I am a PhD student at the University of Surrey.
My name's Motte. I'm currently a fourth year MN student in electronic engineering.
We're deliberately introducing energy barriers at the contact at the source, just as in a source-gated transistor. And we're also using multiple gates to control the injection at the source and the charge transport across the semiconductor towards the drain. By separating these mechanisms, we're able to precisely control the behavior of the device, leading to new ways of operating thin film transistors. And for that reason, we've called the device multimodal. The two types of control electrodes in the transistor serve in fact very different functions.
CG1 is the charge injection control gate, which controls the magnitude of drain current, and CG2, which is in the channel, controls the switching of the device from on to off without affecting the magnitude of drain current at the output.
So that means that we can have the transistor off by controlling the channel conductance, and when it's on, we can program how much current flows through the transistor independently by controlling the potential on CG1. This gives us a lot of benefits, and the most immediate one is the linearity of the input to output behavior of the device.
Linearity is one of the most desirable circuit features. We are able to design the device in a way that allows for a linear dependence of output on input. We can elicit a directly proportional dependence of output on input.
Even when operating this device in saturation, we're able to generate constant transconductance.
Because it has constant transconductance, when you use the MMT in common source, it results in a much lower total harmonic distortion value than for an equivalent TFT.
So the device's linear behavior allows us to create relatively complex circuit functionality with very few circuit elements. This is highly important in thin film technologies because, as we know, the more complex the circuit, the lower the fabrication yield becomes. And then we show a very compact digital to analog converter.
You're able to perform multi-level logic and multiplication. You get this functionality that typically would take very large circuits in a single device.
In principle, the role of the channel control gate is to simply turn the device off and on.
Because we were working in polysilicon, the device was subject to the Kink effects. And an interesting property that we found is the ability to operate the device in a region where the Kink effect does not affect the characteristics or degrade them in any way.
A byproduct of the device construction and of the two independent mechanisms of control,
we can switch CG2 much faster than other contact control devices, and in some cases, ohmic contact devices.
But perhaps one of the most interesting features of the device is its ability to operate with great benefits in a floating gate configuration. So floating gate devices have been used in digital and analog memory. We can drastically remove the parasitic coupling to the drain and its effect on charge injection. We're able to protect the source injection area from the effects of drain field by shielding it with floating gates above the channel.
Because CG2 does not control or modulate the drain current,
the upshot is that we get very good output impedance from these devices and potentially very high gain, which is not the case in conventional contact control transistors especially. And this is very powerful because analog charge storage on floating gates is highly topical now for all sorts of AI, neural network, decision and classification circuits.
You can start looking into other types of devices where you can sum different signals on a single floating gate, sum potentials and replicate neural function.
And the floating gate multimodal transistor would be an elegant solution for thin film AI hardware. At this stage, we're just presenting the potential of the structure in compact, analog and mixed mode circuits implemented with thin film transistors. We have recently been awarded over £1 million for a 5-year project to take this research further, and we have a very broad range of collaborators, but I strongly believe that the true potential of this structure will only be realized with input from the larger scientific community. And so I would be very happy to know your thoughts about potential applications, integrating with other types of devices, and filling a gap where there is one, especially in thin film technologies.
Because it's material agnostic, you can fabricate these devices in a number of low-cost methods.
But there are plenty of opportunities and challenges in implementing these with the upcoming set of materials, and we're very much looking forward to this next step.